anyone's wondering if you're on the right webinar, yeah, this is the RAINA RDH joint session on defining drainage. And this is just part of the fine print that we should have in our presentations these days about, don't rely on this exclusively. Get some more detail if you're going to make any important decisions. But now I'm going to turn it over to Todd, and he's going to let us know more about RAINA for those of you who might not know about it.
Terrific. Thanks, John. And thanks, everyone, for attending today. Super excited here. This is part 3 of the deep dive in a Rainscreen series that RAINA has been able to collaborate with RDH on. And the first 2 programs were excellent, as I think today will, as well as our future programs. So I think many of you are familiar with RAINA, but just quickly, just for those of you who are not, the Rainscreen Association in North America was founded in 2020. We've grown quite quickly into a very kind of dynamic, active organization, committee driven, touching a lot of different things. But ultimately, our mission is to work together with our membership, with the industry and the trade to be the recognized authority in Rainscreen wall assemblies in North America. And our vision is really to be recognized as that authority and to support performance-driven Rainscreen assemblies that contribute to more durable, resilient, healthy, energy efficient, and safe buildings. And so we can move on to the next slide, John. Sorry. So, as far as kind of our activities, we've had the pleasure of John participating on our definitions committee, which has been great. We have our performance committee, we have education and training committee. We now have just launched a retrofit committee to talk about kind of the application of Rainscreens to reapply or to reclad existing buildings. So lots of things going on. And so being part of our association here can really help to influence the industry to kind of stay up to speed on what's going on. To be part of education and training series such as this, we've actually just launched a hands-on training program with some of our members, with the masons, with the carpenters, and with the sheet metal workers, and we're looking to do more of that in the future. It's just also a really great place to kind of connect and to network and to really promote your services as well as your products. And so it's a diverse group. It's not just a manufacturers association. It is inclusive of design professionals, consultants, contractors, trade associations, really trying to bring everyone together to kind of help build better Rainscreens. So you can move to the next one. And so we definitely encourage people to check us out and to join if they can. We have different membership levels for different types of organizations and partners. So, you can go to www.raina.org to find more information, but we'd love to have you be part of it. And here's a QR code so you can stay up to date. We do have some quarterly newsletters that come up that talked about what's going on in our committees and within the organization. So that's a great way to just stay connected and to figure out when and where is the right time to join. But I'm going to now hand it over to Dr. Straub for him to do his magic. This is going to be a great program, and I will be managing the Q&A. We're going to try to save most of those questions till the end, but if there are certain ones that I think make sense to pop up, I'll try to feed those through to John as we go. But please, again, use the Q&A function for any questions, and we'll try to get to all those at the end. And if you have any sort of housekeeping requirements, the chat function would be the right tool to use. But without further ado, I'll hand it over to John.
All right. Well, thanks, Todd. Yeah, I mean, it's kind of, I think it's telling. We have a Rainscreen association, and it's because Rainscreens are very common nowadays. We talk about them a lot. And part of the goal of this webinar series is to, I guess, reevaluate what we think we know about them to make sure we're on the same page. That's why we have something as arcane as a definitions committee at RAINA, is that actually it turns out to be kind of important. There are things we talk about that maybe one manufacturer has a different idea than the other. The code is a different word to use for it than the common language on the street. So we've been breaking this down. The first 2 sessions were, Graham French did a really good 1-hour overview of the whole topic area. And you can go and find that online, and you can watch it if you've missed it. The last one I did was about more of a history, about how did we get here, what words are we using. And so that's for someone who's actually quite interested in where we got to and where we're going. This is the first session where we're going to dig into some of the actual practical decision making that we have to do when we're specifying, designing, building rain screens. And so we quite deliberately started with defining drainage as our first get in on the meat of it presentation, because drainage is really quite important. Now, I always have to put a couple of slides in here when I'm discussing rain screens, is just to be clear that rain screens are one type of the three available rain control strategies. So in one slide, let me summarize here. There are three approaches to rain control or rain management so that water doesn't go into the building. The oldest one is labeled number one here, which is the storage approach, where it accepts that water will pass through the outer skin and absorb it into the masonry. And then before the water wicks and does damage on the inside of the building, it evaporates and dries out. That's its way of working. And obviously from the images you can see, this is an old thing, old buildings. We still build a few like this, but not a lot. But Todd mentioned that a retrofit committee at RAINA, and that's because there's a lot of these types of buildings, which if they don't have architectural beauty on the exterior, it's pretty clear that one of the best ways to retrofit is to apply a membrane for air and water control, add a bunch of insulation to get good thermal control and environmental performance, and then put a rain screen cladding over top of that. That is a pretty common approach. And what that's doing is taking the mass wall rain control approach and making it a drained approach. That's the number three highlighted in red. Now, even though you may have a rain screen system on your building, most buildings have large areas that use what's called the perfect barrier approach, or even a face sealed type of perfect barrier. And those are the glazing units, the low slope roof, and sometimes certain types of like large format precast or foam filled panels. These can be face sealed. Functionally, they work great, but you still have drained approaches where you use small panel claddings at joints, etc., window frames, and all the rest. So we're going to focus, of course, on rain screens. And the examples shown here are lap siding, panel cladding systems, and even masonry veneers if done right. And I'm going to explain a little bit about how those are rain screens and what that means. So rain screens have become very popular in the last 50 plus years, but really have accelerated as a category that people understand and apply in the last 10 to 20. And this is because rain penetration of the building enclosure and the building itself has remained a big problem. And it's one of those problems that we just haven't been able to find easy answers to. And rain screen approaches to rain penetration control offer a reliable, high performance way of managing rain penetration. It also happens to be that the rain screen approaches are the appropriate ones for lightweight cladding systems made of a whole wide range of materials, from terracotta to ACM to slate. And those types of popular cladding systems are just natural pairings with rain screen rain control strategy. So the rain screen definition by RAINA is an assembly applied to an exterior wall, which consists of a minimum of an outer layer, an inner layer, and a cavity between them, sufficient for the removal, passive removal, of liquid water and water vapor. So just bear that in mind, because I'm now going to say, today's session, we're going to look at the cavity between them and drainage as a mechanism for the passive removal of liquid water. That's why we're going to talk about drainage and what we need to do. So if we were to draw a conceptual rain screen drawing, we would have a cladding, we would have a drainage and ventilation gap, we would have an air and water control layer, maybe a WRB and an air barrier from code language. Also today, we routinely have continuous insulation placed on the exterior of the enclosure support structure. So I'm just showing you those components. You'll notice we have things like flashings, very important, and drain openings and vent openings. So that's a more nuanced way, or more not nuanced, more complex way of looking at all of the layers. It's more than just an outer layer, an inner layer, and a gap. There are more things that a wall does than just control rain. And so that's what rain screens apply to, just how they control rain, whereas we have other things we have to do. The gap in the definition between the outer layer and the inner layer is there for a number of reasons. And I'll give you 4 reasons that are almost always raised. One is to avoid bridging of water droplets of that cavity or gap. Another, the focus of this presentation, is to allow drainage of water. But the third one is quite important in practice, and that is to accommodate tolerances and movements between the cladding and the backup. And so it's a pretty important function of that gap, but it's often overlooked. And then we also have, finally, the passive removal of water vapor in the definition is to allow ventilation drying, to vent air from outdoors through what could be a wet cavity to take that water away. That's going to be the topic of the next session, not this one. Now, if any of you, I know some of you were at the last session about the history and how we came to rain screens. You may remember that drainage as a way of managing rainwater is actually a relatively new concept. And in the building industry, if it happened 30 years ago, it's relatively recent. And so this is an example of a 1993 US government document by well-known Dr. Persili, who gave guidance to say, you need a second line of defense combined with a drainage system. We still didn't have a WRB. Water resistive barriers had not been named or identified yet, but drainage at this time was becoming obvious to some practitioners and, in fact, some government guide document authors. So why drainage? It's worth just pausing for a moment to understand. So here's my simplified enclosure, outer layer, inner layer with a gap. If water gets through either open joints, which I'll call an opening or intentional opening, or an unintentional crack, which could be failed sealant, a literal physical crack in between mortar and brick or something like that, water can get in just by gravity. If water's running down the wall, water can get through the cladding and then run to the backside, the inside facing surface of the cladding. And so on the left-hand side, I'm showing water droplets running down the back of that cladding. And if you shape the cladding right, as I have, and you have a flashing, water will cling by surface tension along the bottom and then drip off and go back to the outdoors. So that's effective drainage, to say that water that leaks through those openings can be rejected back to the outside without challenging the rest of the wall system, and certainly not leaking to the inside. If you don't have drainage, in the exact same scenario, if I provide a block, and as you can see, I've chosen a checkered egg to plug up that drainage gap, now those droplets will accumulate and you will build up a head of water. Hydrostatic pressure is what results from a head of water. If you have 1 inch of standing water, it produces a head of 1 inch. It's complicated. Now that turns out to be 1 inch, turns out to be 250 pascals. And we often use pascals as well in rainwater penetration tests and so on. So that standing head of water means that it takes a very insignificant opening or crack on the inner layer to allow water to spurt through under pressure. Now, if you had, let's say, a staple hole, that would leak because it would have water pressure on it. So if you were to use a polymeric house wrap and attach it to the substructure with, say, staples, that would produce a whole bunch of holes, thousands of holes. If you have blocked drainage, you build up hydrostatic pressure, and every one of those holes is now at high risk of leaking. It's not a certainty, but it's very, very high risk. If you have any kind of flaws in your inner layer, or what we'll eventually talk about is the water resistive barrier, that hydrostatic pressure will drive water through. You remove that blockage, and gravity will drive the water out and remove that pressure. So while drainage is simply removing water that penetrates the cladding using the force of gravity, the reason that's so important is that it avoids any kind of buildup of pressure. And hydrostatic pressure is really hard to avoid leaks on the way we build our walls. Now, an obvious question that comes up a lot is, how big should this cavity or gap be? And the answer is, it depends. It depends on which of those four functions I listed earlier, bridge, drainage, ventilation, or tolerances, are you focused on. There are other things that we worry about in gaps as well, like fire. But let's just deal with the first one, water droplets and bridging. On the left-hand side, we see our system again with the water running down the back of the cladding, the inside face of the cladding. And provided that the gap is larger than the size of the droplet, the water will theoretically stay on that side and it'll just run down and you can get rid of it at the base. Now, if the gap gets close to the water side, at some point, the water droplet could get large enough that it'll jump over to the other side, and now you will have water bridging over the gap. And so to understand how big of a gap we need to avoid bridging over to the other side, you would have to go look at the size of droplets. And so I've spared no expense here to conduct this sophisticated experiment where I put droplets of water on a sheet of glass. And the droplet gets the biggest just before it begins to run downhill. And so we can play around with a bunch of different types of surfaces. Glass is the purest form. I'm showing it here. And from that, we can then look and say, how big does the droplet normally get before it begins running? On the left-hand side, you can see I'm using a commercially available water-resistant barrier with a polyethylene facer. You can see the droplets there are actually a little bit larger than you get when you get glass. And when I'm looking on the right-hand side, I'm looking from the top down, and we're seeing the size of that droplet. And I'm seeing this is one of the largest droplets I was ever able to photograph. And so they're all under 1/8 of an inch, under 3 millimeters. But so that gives you a sense, and I'm sure we can have a competition and people can try and measure fatter droplets and do things to them. I look forward to your experiments showing how big the drops get. So really, from doing that kind of stuff, it's pretty simple, but also pretty clear that once you have a gap of over about 1/8 of an inch, water's not going to bridge across it. But we could also ask, why do I care with water bridges across? For a number of reasons. One reason is that I have a water-resistant barrier there. Now, in Europe, they don't as often use water-resistant barriers, and they rely on the cavity itself to stop water from jumping over. But in North America, we would always have a WRB there by code and good practice. And so do I care if a droplet goes over? Not very much. But we'll find out that also that from experience, we also learn a lot of water just gets right over the gap, even if it's a 2-inch gap. by penetrating at penetrations to the walls, like other systems, like windows and doors and such. So then the question is more, okay, well, I want to be able to provide drainage, meaning water that comes in will drain by gravity to the bottom and then be rejected. So how big of a gap do I need for that? This is the first sort of topic that people researched and studied. And the short answer is that the gap can be actually quite small and drainage will still occur. And this has been, on the left hand, we're seeing some images here from the Natural Research Council of Canada, where they did a bunch of research in the 2000s. Building Science Corporation, we built field huts and had stucco and vinyl siding applied to see how small of a gap we could get to and still allow drainage. And one of the surprising outcomes of that research was that the rate at which water could drain between two sheets of paper that had stucco over top of them was astonishing. Like water would drain like crazy. Now, those gaps that drained were smaller than the gaps required to stop bridging. So if you want to avoid water bridging from the back of the cladding to the front of the WRB, you're already in the 1/8 inch and plus zone. So you don't have to worry too much. You've got drainage. And since that time, lots of walls have been tested and investigated. Recently, even in Europe, they've started to consider using water-resistant barriers, and that means that they're starting to look at the drainage capacity of small gaps. 1/8 of an inch or less, I think, would be considered small. Now, if I have a gap that's small enough that water bridges it, it could actually hold water. And this is because of the capillary force or capillary force, depending on how you're supposed to say it. So water is attracted to some materials. Those materials are called hydrophilic. Materials like high density polyethylene, which is what they would make Tyvek out of, or the polyethylene facers that they would use on many peel and sticks, those are hydrophobic. They won't attract water. But materials like glass and most metals and fiber cement and terracotta all attract water. And so if the gap is small enough, you can get water stuck, held in a gap by capillary forces. As I've shown on the left, I've got a couple of droplets of water. So I did some experiments on that as well. So this is a 0.04 inch gap. So how do you make a gap consistently that small? On the left-hand side of this screen, you should be able to see what's a feeler gauge. So it's actually a precision-made piece of metal that is exactly 1 millimeter or 0.04 inches in thickness. So with two of those clamped between a glass, I can be pretty confident that that's the gap size. And so then we insert water in there, and you can see that there's a couple of droplets that are held into that space because it's quite small. A dime is about a millimeter. A dime's a bit thicker than a millimeter. Now, here's some images, action shots, if you will, where when you add enough water into the gap, the droplet grows in size until it begins to break free and fall under the force of gravity. At the bottom on the left side, you see some of the droplets are just sitting there. They're hanging on by capillary forces. If they get any larger, they will drip free. And that's what's happening on the right-hand side. I've injected enough water into a droplet to make it fat, so it runs down under the force of gravity, it runs into the bottom, and then the water droplet runs free. So I'm going to show you a video of that scenario. So those are photo stills out of that video, but you can just get a sense of when I put a droplet in on the top, and this here we have HDPE as a backer. if the droplet's small enough, it doesn't flow on its own. So those are about the droplet sizes that if you can see they're starting to move. But there you'll see a droplet form. When a couple of droplets get fat enough, they move quickly to the bottom. And when a droplet is held at the bottom, it'll eventually be filled up so much it'll blurp out of the gap altogether. So this is all just to say that if you're interested in drainage, the gap doesn't have to be that big, and not too much water will be held. So, oops. So I'm just having a few, oops. There. So we know that water in most of our gaps are larger. If only they're larger because we want to do other things like dimensional tolerances or ventilation. So the gaps are large enough, and we have a WRB on the inside layer. So we have our outer layer, our gap, our inner layer. Our inner layer is the water resistive barrier. And that water resistive barrier, as you can see, water can run down it as well until it gets to the flashing that directs the water to the outside. Now, I mentioned that even if I have a large cavity, 2 inches, 3 inches, water can get to that WRB at penetrations like windows and balconies and air conditioning sleeved units and so on. In fact, in practice, although this hasn't, it's hard to quantify this, in practice, that's almost where all the water leaks anyway. And it's because the water is going deeply into the assembly and then beginning to drain on the water resistive barrier. So we really should probably not describe it as a drainage gap. We should probably call it a drainage surface because the water's not falling through the gap without touching the sides. In almost every practical situation, the water is clinging to one surface or the other. And so this sort of observation is also what led Joe Stieberich to define the term drainage plane, which is like the water resistive barrier, that surface on which the water is actually running. And so this is the surface that we spend a lot of time and effort on, I think, in specification and design, making sure that we get it so that it is durably water resistant and that it integrates well with the openings and the flashings to get the water out again. So what's not as well appreciated, I don't think, is that we've now have lots of wall systems where we actually have insulation put outboard of the water resistive barrier. And so when we think about, as a minimum, the RAINA definition, outer layer, gap, inner layer, well, in many practical wall systems today, we have the outer layer, a gap, insulation, and then the water resistive barrier. So that means that we now have layers 1, 2, 3, and 4 are listed on this image as places or surfaces along which water can drain. And by adding this layer of insulation, it actually meaningfully improves the drainage ability by keeping the water away from the WRB for longer. And that means that the WRB is not challenged as often with water for as much water for as long a water, and that improves its performance. So as a comparison of this, a few years ago, we had Rockwell sponsored a test of open jointed cladding systems and how much water would get through them and onto the insulation. And so this is our open jointed cladding. We used plexiglass so that we could see a little bit more about what's going on. But we had 6-inch wide strips with a 1/2-inch joint between each. So that's a pretty open jointed cladding system. Then we had a 3/4 inch gap, and we used 2 different types of insulation. and we used standard ASTM spray racks, calibrated spray racks that sprayed water direct at this cladding system. So we also weighed the cladding system while we were testing it, so we could see how much moisture was actually being picked up. But more interestingly, at the bottom of this test wall, we would measure in trough number one the water that would be drained off the front face of the cladding. And in trough number two, we would measure the water that was drained down the back face of the cladding. Trough number three measured the water that came off the front face of the insulation. And trough number four measured what got to the WRB. And the results showed that actually, and this is in other systems too, a surprising amount of the water is drained on the front and the back of the cladding. In fact, the majority of it. And when you then look at the insulation, the front face of it drains the majority of the rest of the water. Very little water actually made it back, to the point where we really never measured water at the WRB layer. It was only that it was obvious that there was some droplets back there by visual inspection, never enough droplets that they would run down into that trough. So we did 15 tests with variations, but suffice it to say, the addition of that insulation layer dramatically reduced the amount of water that the WRB was exposed to. So one of the things that one has to recognize is that small cracks allow water to leak past cladding. I think everyone gets that. That's why we're paranoid about rain penetration. Small cracks will let water in. But what's not, the counter side is that small gaps will also allow drainage. And that's what some of that research and testing has shown, is that, yeah, you only need an 1/8 of an inch or so and the water's going to come out again, no problem. But in the range of an 1/8 of an inch would be totally safe to stop, to allow drainage and to avoid bridging. And even a 1/16 of an inch will allow substantial drainage. So we're normally going to make gaps more than that size for other reasons. So drainage isn't really the challenge. Now, we now have new code requirements that we need to provide various size gaps depending where you are, in which code body made the determination. The International Building Code in moist or marine climates requires now a 3/16 inch gap behind stucco. And it's there and then it says you're supposed to test it with a drainage efficiency of 90% as measured in accordance with ASTM E2273. So we can make these gaps out of more than just air. On the left-hand side, you see wood furring strips, which is widely used in low-rise wood frame buildings. On the right-hand side, we see metal subframing of one type or the other, Z-girts on clips or something like that, which allows an air gap to form. And you would have a hard time making a gap of only an 1/8 of an inch, just from a dimensional tolerances point of view. Now, in the middle of this screen, we have like a number of different approaches to providing a drainage gap. And these are polymer entangled meshes at the top, or polymer formed sheets at the bottom of different types that provide gaps that let water drain unobstructed. There's no way that you will build up a hydrostatic pressure in these products. Even though they're not as open as a full air gap, they certainly let the water flow under the force of gravity. There hasn't been as much research into these products, but they certainly have been successfully used on the marketplace in low-rise buildings for 20 some years. So let's just talk a little bit about how those drainage gaps and some of those measurements I talk about play a role in design. If we look at on the left-hand side, design number one, we have some sort of a thin cladding, and it's installed over furring strips, metal or wood, installed vertically. That means that drainage has a full, somewhere between 3/8 and an inch and a half of drainage space. So water can drain down the back of the cladding, the front of the sheet there, the WRB that's installed, until it gets to the flashing and then be rejected outwards. So that works like everyone would expect. Now, if you were to use a flat sheet of cladding and attach it to a horizontal, in this case, it's showing a hat channel of metal, it's pretty clear that there's a pinch point created in design number two. And is that pinch point going to completely block water? It's going to be hard to completely block water, but it's going to be easy to think that water will constantly sit on that top edge. And that might result in corrosion of the metal or decay of the wood or discoloration of the cladding or damage the cladding, depending on a whole bunch of things. So therefore, you would want to encourage drainage past that spot. So even though someone might look at that drawing in design number two and say, oh, look, it's got the same size of gap as number one, it's not true at all, because the gap is defined by that blockage that forms at every furring strip. So nowadays, we can actually buy hat channels that look just like that are perforated. They've actually pre-punched holes in them so that the water can flow through. Massive innovations. But that is, for example, one of many answers to ensuring that your drainage cavity is not blocked. The focus on, is it a half inch or is it 2 inches, often misses the most important aspects, which is, but how continuous is that drainage gap? That's the critical part, because it doesn't make much difference between half and 2 inches from a drainage perspective. Now we get to the drainage cavity of number three, and this one's maybe not as obvious to see, but if you have corrugated metal cladding, as you might have on a car dealership or something like that, that corrugated metal cladding allows water to drain past those horizontal Z-girds. It's if you were to pour water in the top of design number three, it'll all come out. So that's a pretty well drained system, even though it's just corrugated metal placed on a wood or metal hat channel. Now, number four is, again, what I talked about in number two. It's just that, okay, we've added perforations so water can drain through those perforations. Another approach would be to use a combination of vertical hats and horizontal hats. Twice the material, twice the labor, but it would therefore make sure that you have an unimpeded depth of the vertical hat section available for drainage downwards. Now, again, I'm not going to just tell you what we have answers to. I'll tell you a little bit about what we don't have answers to. So if you look at lap siding, which we have a long history of use on low-rise buildings, it actually doesn't quite meet the requirements of a Rainscreen, or maybe it does, maybe it doesn't, because at the laps, there's not much of a gap. So inner layer, outer layer, and a gap. But the way it works, of course, is that water can drain out between those laps, provided those laps have enough roughness, imperfections, warping to allow water to drain out. It can actually become a problem on the image on the right-hand side. That wood is so perfectly cut and planed is that if someone were to apply a thick layer of paint over top of that wood siding, it could actually trap drainage. Now, today, we would be putting all of this lap siding on vertical furring strips. And that would basically completely alleviate any concerns about drainage. But the reason we're putting it on furring strips actually isn't about drainage. It's about ventilation. So it's about ensuring drying of the back of this cladding, not just drainage of the system. And we'll look at that in more detail at the next presentation. So drainage testing is becoming a bigger issue because of the focus on drainage and rain screens. One of the ways that you want to demonstrate that the design that you have, whether you're a manufacturer or the architect of a new building, you want to be able to identify that it does drain. And so we need to have some way of measuring that. Unfortunately, the first type of standard that has entered into the available types of testing is the ASTM E2273. E2273 is explicitly a method for measuring drainage of EIFS systems. And it's worth noting that it came out in 2003. And this was a response to the many problems they had in North Carolina and other areas, but North Carolina was the big area where they used face sealed claddings that had no drainage at all. Water would leak through at various points, particularly windows, decks, chimneys, etc., and it would be stuck behind the EIFS system. So they switched to a drain system to manage that, and they also then had to develop a test to prove it was drained. And this is what this test is about. Now, it's been renewed in 2018. That's why the dash 18 on the standard, but it doesn't really measure efficiency unless you think about it in a very specific details of the test. And so you have to be careful about using this test. Because it only has meaning specifically for this test. So there's a 24-inch wide slot in a 48-inch wide test panel. Water is applied for 75 minutes, and you measure how much water you apply, you measure how much water comes out, and the difference is the efficiency. So if you put in 100 gallons of water, well, actually, it's going to be more like, let's say we put in 2 gallons of water, and you only measure 1.8 gallons of drainage, it means that it's 90% efficient. So it doesn't mean that it didn't drain. By definition, the fact that they put water in and water came out says it drains. What happened to the water that didn't drain out? It's absorbed into the materials that line the drainage gap. It's hung up in water droplets on both sides of that. And it could also potentially be leaking into the living room. So the test doesn't talk about any of that. It just says that 90% of the water you put in comes out. And that's what they deem to be efficiency. But that can be very misleading about what the actual concern is. A brick veneer with a 2-inch airspace is able to drain very effectively. You can pour a lot of water in. However, it would fail this test. It would fail it dramatically because masonry, the veneer, stores water. And so if you pour only 2 gallons in a 2-foot wide slot, most of that 2 gallons will just be absorbed, keeping the dust down in the brick. And it doesn't mean that it's not a well-drained system. It just means it's a cladding that stores lots of water. So we're going to have to sort this stuff out in the industry to be able to distinguish between an ACM cladding, a terracotta cladding, a fiber cement cladding, a wood cladding, and an EIFS cladding, because the storage is not a defect, it is a characteristic of the system. So here's an example of some drainage testing done many years ago by John Smeagol for his master's thesis, which focused on drainage in wall systems. And again, we weighed the wall so that we could measure how much water was stored and measure it very accurately. But we also weighed the water that drained out, and so that we could at the same time measure water in as water out. So This is kind of what these tests look like. The blue line in the bottom left chart and on the upper right drawing section is we're injecting water at a steady rate into the top of the drainage gap. So it's difficult to choose 24 inches because so we just chose the whole width of the panel. And you run the water in for a certain amount of time. How long? Well, it depends on how much water, how absorbent the cladding is. The green line is the rate at which water drains out. At the beginning, water doesn't drain out. It just makes droplets on the surface of the WRB and or back of cladding. But as you continue to put water in, then the water will begin to trickle out the bottom, but water will be absorbed into the cladding if it is a moisture absorbing cladding, like terracotta or fiber cement. But no, essentially no water will be stored if it's an ACM, as an example panel. So then very quickly in an ACM, the green line, water comes out as quickly as water goes in. Whereas if you're doing a brick veneer, the water going out equaling water in will take hours. And so eventually, though, it will reach equilibrium, and now we'll know how much water is stored after drainage. Again, this test would only tell you if water leaks to the inside if you actually went and observed it. So you need to have a way of saying, yeah, and water didn't leak. So all of the drainage, all the water I put in and come out is accounted for. It's either stored in the materials or it drained. Now, this is just an example of an actual measured result for a system. And 15-minute test here. This was a cladding system with little storage. And so it took almost no time at all after the water started going in at about minute number 1 and a bit on this drawing, on this graph. Very quickly, the blue line and the green line were the same. Drainage began, and we ended up with within 5 minutes, drainage and water entry was about the same. So that's and then there's no doubt the system drains because the water in equals the water out. That observation that by putting water in and having it come out in the same quantity or the same rate means the wall is perfectly drained can be used as an on-site quality control test as well. This is not an ASTM standard test. This is, or maybe another simple test method, I guess I'll call it, where we use this as a way of testing things like drained window openings, the rough openings of windows. The drained, in this case, we're testing the drainage capacity of a 2-stage joint in a precast concrete wall system. And the joint in a precast system should be a drain system, should be a Rainscreen approach. And here we are inserting a small stainless steel pipe to the gap. We are injecting the water. If you can just see it in the upper left, we have a large syringe, a veterinarian grade 60 cc syringe, and we inject the water and we make sure it comes out where it's supposed to come out. If the water doesn't come out or the water enters the building, we call that a fail. If the water mostly comes out of the weep hole and nothing goes into the building, we call that a pass. But you have to use a bit of judgment here as to whether or not you would expect much storage. So that is a very practical way of assessing on a job site in a not very destructive or damaging way. Did you install the subso window flashing in a drained way? Similarly, if you're not sure whether a cladding system has drainage, you just get a bucket or a handheld bucket, and a beer pitcher has been used in the past, and you pour half a gallon of water into the gap over a period of about a minute, and that water should come out at the weep holes and flashings as the design intended. That's a drainage test, and if the water comes out, it's drained. So let's talk a little bit here now to close up here. What are the practical implications of this type of knowledge? So small gaps drain, okay, but you'll need a gap of more than 1/8 of an inch to stop bridging, And in most cases, in almost all cases of what would be called Rainscreen claddings, to be able to have passive removal of water vapor by that gap, you're going to need a bigger gap. And you're going to find out you need a gap 3/8 inch, 3/4 inch, something like that. So those larger gaps are very common, not because we need them for drainage. They're there because we need them for dimensional tolerances. We need them there for ventilation, not for drainage. And we'll have to talk about those other ones. Now, one of the things that we don't have good answers for is how often do I put flashing in a building? On the right-hand side, I'm showing you a 4-story building. And at the way it's drawn, there is not a single flashing to direct water out. The water that enters that gap drains down the back of the cladding and comes out at the bottom of the building. Theoretically, that could be a totally acceptable design from a drainage perspective, but we regularly break up our Rainscreen claddings on a per floor basis and have flashings every floor to reject the water to the outside. Is that necessary? In most cases, it probably isn't. Most claddings don't leak enough that they require flashings at every floor to avoid overwhelming the ability for the flashing to drain water. But we don't have any good guidelines on that particular discussion. And the reason we're putting flashings at every floor almost always has something to do with managing building movements, especially floor to floor creep and beam sagging, providing fire stops floor to floor. The reason we use a lot of steel flashings that go across the cavity is to provide a fire stop between floors, etc. So again, if we have to be careful that we don't think that we're providing flashings every floor because it's needed to let the water out, because that might limit our ability to come up with better designs for a particular project or a particular application. So as we go through these other issues, such as ventilation and fire and movement, we'll be able to have a better picture of why we would choose a certain cavity type, flashing design, cladding attachments, etc., to be able to meet all of the requirements for an assembly, not just the one. And while drainage is the most important, one can argue, function of a Rainscreen wall system, it's often not the reason that we have big cavities. There are, ventilation drying and dimensional tolerances are really important. And so without understanding the full picture, you can't explain the design choices that we make. Now, if you're somebody who's involved in either the construction or inspection of construction, the big takeaways here are don't block gaps, don't block drainage. And by blocking drainage, we don't mean that the cavity goes from 2 inches down to 1 inch. That's not blockage. It's when the 2 inches goes down to a 25th of an inch or something like that, because that starts to be pushing your luck. And so be aware of what it means to block drainage. Something though, because drainage is so important, confirming drainage during construction by visual inspection, or if not visual inspection, pouring beer pitchers full of water into the cavity or syringes into joints is recommended as a way of confirming that the designed intended drainage is being delivered. It doesn't have to be a fancy test. But of course, regardless of all of this discussion, we still need that continuous water resistive barrier as the inner layer. That WRB needs to be there because we can be almost certain that water will cross the cavity, not necessarily by bridging across a gap, but because of water clinging to the surface of things like through wall flashings, windows, doors, balconies, cladding attachment systems, etc. And so that WRB is our last line of defense, our inner layer, and it should be water resistant and not have any holes in it. So I've mentioned ventilation numerous times through the presentation because actually it's a really important aspect of the true Rainscreen system. And I haven't talked about it anything all because we're going to do that in the next webinar on November 15th. And so this is your teaser, unless you're binge watching this webinar series. And then you can just scroll to the next one because you're watching it sometime after November 15th. There's lots more information on Rainscreens, both at the RDH website and on the RAINA website. And I strongly recommend you go there. I think Lynn is going to post something in the Zoom chat for some resources about where to go to find some of this information if you want to read ahead. And please provide that feedback to a survey that will pop up on your screen into this presentation. And now, oh, look, it's popped up on mine. So I guess I'm not going to vote because I don't want to disturb the veracity of this vote. But I'm going to see what kind of Q&A questions we have, or if Todd, if you have some that you'd like to know.
Yeah, terrific. And just first of all, thank you, John, for a presentation on drainage today. This was not often do we get an hour to learn about moisture coming down a surface, but it's you always make it very entertaining and impactful. So there were a number of questions along the way. I'm going to try to filter them to kind of what I think would resonate well. You were just ending on just concerns about reducing maybe the gap from, let's say, 2 inches to a nominal amount that could be impactful. There was a question about bug screens at the bottom and the top of the systems, and oftentimes those bug screens will reduce the drainage capacity of those walls. So I think that's an interesting question to start with based on kind of how you ended, and if you could speak to bug screens and the integration within these systems.
Sure. And in fact, it's also one of those things where like the spacings of flashings, I don't actually have convincing scientific evidence. Although I might be one of the few people who's actually measured the pressure drop as a function of airflow through insect screens. And we did that through a whole bunch of different vent openings and so on. But the short thing is that airflow is significantly affected by the design of those screens. So ventilation, next seminar. Drainage is only partly affected, but it basically means that if it's blocked, and it often would be by like dust or dirt or dead spiders, the hydrostatic pressure that builds up will relatively quickly overwhelm that and it'll leak out. But just be prepared for the fact that around where those screens are, you will have a bit of hydrostatic pressure. The good news is that usually where we have weep openings is where we have flashings, and flashings have to be waterproof anyway, because to be able to make the water flow horizontally in the direction you want it to, towards the outside, you have to build up a bit of hydrostatic head. So meaning that I wouldn't freak out about the screens and their effect on drainage as much as I would be concerned about their effect on airflow. And that we don't have a good answer, and we'll talk about what we do have next time.
Gotcha. A couple of others, that I think are very relevant here is the discussion around fibrous insulation within these cavities that might get wet and either absorbing water, and then if they are absorbing water, what is the drainage considerations that we need to have to address those things?
So the most common, if you're talking fibrous in that these polymer mats, right? The entangled mesh, I think, is the generic term. Bridging capacity is increased. It is. And again, I guess one of the reasons I'm not that worried about that is that the water crosses over to a WRB. So the WRB is supposed to be there to get wet anyway. I guess I'd also say that it's not just the bridging potential, but the nature of those things means that more water is likely to be stored in them. And that might be a concern in some designs, not well looked at or answered. But that fibrous entangled plastic mesh absolutely guarantees no hydrostatic pressure buildup, which is job number one. But bridging can happen much more often, and it'll hold a bit more water, and that may matter to some people on some walls.
And what about with those fibrous mats, any impediment to ventilation? Is there any concern that you need to have with those mats in that regard?
Yeah, the concern you have to have is that it impedes ventilation. And how much does it impede ventilation? Fair bit. We don't have a lot of good, I don't have a lot of good information about that. I have tested dimple sheets, and dimple sheets, because they're more rigid, they definitely reduce the area of ventilation, but what they do relieve, what they remain behind is, open, right? Because it's a rigid plastic. With the mesh, I haven't ever tested that. So I don't know. But, from what little we've done, it does seem to be a pretty significant reduction in airflow if you need that.
Okay, so taking it back to, let's say, fibrous insulation versus a fibrous mat, I guess there was a question about any sort of moisture absorption in insulation that
Right.
that needs to be considered and managed. And if insulation does get wet, how quickly does that, or what are the concerns there, and how do we dry that out or drain that out effectively?
So that's a kind of was one of the driving forces behind us doing that measure, those tests that I indicated here, the drainage balance comparison. And basically, that's why we compared it to a stone wool insulation and a foam insulation. And remember, stone wool insulation is highly hydrophobic, and so it doesn't really absorb water. And that's what these tests also showed. That you can download that report and look at it. It's literally almost no difference. A little bit of water is stored in all the walls, just as droplets on surfaces, and it all dries out pretty quickly. So as long as you've got that, more than an 1/8 inch gap or something like that, it's just a non-issue.
Okay. What about in between furring strips and WRBs within Rainscreen? And is there any concern there about moisture getting trapped at that location? I think there's manufacturers that try to minimize the touch point with the WRB. How do we address that, or is that a concern that we need to be aware of?
Interesting question. So on one level, look, if the batten or the furring or the strapping, and there's a whole bunch of words for the same thing, if it's vertical, I'm not at all worried about it, because gravity is a strong force driving water droplets down. And the WRB is hydrophobic, meaning it's repellent of water. So water doesn't want to wick into that gap. But I'll go further than that. One of the roles of vertical furring strips in let's say a polymeric house wrap type of a product, which is a pretty common low-rise building system, is that it actually makes sure that where you put nails through your furring strip to attach the furring strip to the substrate, that hole is protected. The furring acts like a big washer, a gushy washer, to prevent water from getting in that space. And that actually improves the water holdout ability of that system significantly, measurably. If you take that furring strip and provide an 1/8 inch gap between it and the polymeric house wrap and still put nails through it, now you've got a hole that water can get to. Now, gravity's still going to want to take it down, but it's much more exposed to wind-driven pressures than if that was actually smushed. I'm using technical language, smushed right tight to the surface. So now, as soon as you go horizontal, I think you realize that a lot of that I just said, it has a different meaning. And that's why those drawings showed a hat section with a bit of an angle, shedding the water away from the WRB. And that would be why with wood furring, we often use 2 layers, like vertical furring and horizontal, to make sure there's a full gap. Or if you're doing horizontal furring, you want to provide gaps. Then you want to provide gaps so that the water, which would be sitting there with gravity trying to get at that joint, is allowed to flow on through. So very different answers depending on whether it's vertical or horizontal.
Yeah, that makes sense though. And I'm trying to pull questions that are relatively close in kind of nature here. And this one I'm just going to read verbatim because I'm not a stucco master yet. But The question is from Brett Lassard, and he says, "Can you please address stucco? In Canada, stucco lath must be 6 millimeters off the wall, and the lath fastened to the sheathing with fasteners that penetrate the sheathing. The scratch coat embeds the lath and may cause bridges to the fasteners." And just wanted, I think that's kind of in line with what we just talked about with the fern strips, but maybe on a magnitude much higher level. But I'm
Yeah,
curious what you have to say.
there's a couple things about that. Like stucco obviously lets a lot of water through, right? So that's a pretty big deal. But what he's describing there is that although the mortar or the stucco going through the lath will plug up a lot of the drainage gaps, you got to just make sure it doesn't plug them all up. So the 6 millimeter, quarter inch he mentions is a little bit on the light side, which is, but that will do it as long as you stop water blocking off the space. And so that's where the products come in. Do you have like quarter-inch furring strips and then the lath goes between them and then the lath sags and blocks off when you fill it with mortar? That would be a problem. So this is where those mesh products come into play, the entangled polymeric mesh. Well, they kind of make sure that you can't compress that lath or push stucco material through the lath and plug it up. You guarantee that it's got drainage. So, I mean, the practical answer is how do you make sure that you end up with that at least 1 millimeter gap to get drainage? And then the next question, assuming you can sort out how to get drainage, now, how much ventilation do you need to make sure that you manage the moisture in the assembly over which you're installing it? Which is what I'm getting at is if you have a west-facing wall that is wood frame and you just do this, you have a huge risk of inward-driven vapor drives taking moisture from the stucco and driving it towards the air-conditioned interior, causing problems. That's when you need more. That's when you need ventilation to solve that problem or some other technique.
I guess that there were questions too on gap size in general, and I'm guessing that you're going to get into that in our next session on ventilation, which might tag this a little bit. But is there a concern about making the gap too big? Was one of the questions. So maybe if you can, I think
that's about what I didn't say, Todd, and I think we can simply say about it today is that of course there's a problem with making it too large. At some point, you're making a home for raccoons. It doesn't have, it's not that big, but even at 2 inches, you're making a home for rats. And more importantly, you're providing now a chimney for fire. So somewhere in that between 3/4 of an inch and 2 or so inches, then you start really creating challenges for fire. And then you have to start really focusing on fire stopping and good fire tests, because that we know we have tests of that show that large of a cavity begins to act like a chimney. When you have a 3/4 inch cavity, not a very good chimney. You'll probably, the smoke will come pouring out of the firebox. But in a building, 2 inches is a problem. So there is a problem with going too big. And we'll try and tell you where maybe happy spots are for different types of claddings in the next webinar.
Great. Couple of questions here, John, on freezing conditions and kind of elaborating about drainage under freezing conditions, as well as any concerns about freeze thaw and managing the gap, kind of in and around a freeze thaw cycle. And, does that gap need to be increased? And if so, how much?
Frankly, I've got zero evidence that's how to answer that question. But my intuition is that the amount of water dribbling down a surface in a moment when the flash freeze comes and keeps it in place, I don't see how that's a problem. So those droplets that you saw running down the surfaces, okay, they've frozen to place. Until what? I mean, as soon as they're frozen in place, it's not raining anymore, right? So we got until it warms up enough that it can rain. And by that time, you're melting the droplets as well, right? So there's just not, I certainly can say I've never had a forensic investigation about something like that. I don't think it's a big deal. But I also can't say I know anybody who's done anything at all to test drainage in walls. I've tested drainage in floors for outdoor systems under freezing conditions, but never a wall.
Oh, makes sense. Just going through these. there was a question just historically, I guess we used to use a lot of tar paper over masonry or board sheathing. And I don't know, I know we went through the history during our last session, but even prior to the use of tar paper, was there, is there any sort of notification or history of drainage problems pre-tar paper? Or were we just like dealing with very leaky envelopes back then that things were just drying out by the nature of vapor open, water open assemblies per
And
se?
air open assemblies.
Air open assemblies.
Yeah, yeah. I mean, the air did a lot, right? So we actually did have ventilated assemblies in the past, but it was air was literally passing through the whole entire enclosure. But that said, yes, we used tar paper and we used it and we knew that we should lap it in a gravity fashion. So the practice totally acknowledged that we needed a WRB. But I want to be clear, we didn't use tar paper over masonry much until quite late. We used tar paper over wood siding, over wood sheathing. I mean, wood frames and wood sheathing as early as the 1890s, documented evidence. And we didn't do that at all until way later into the 60s and 70s. And there's still people who build nowadays in America who don't put building paper or a WRB of any type over the masonry backup wall. So the paper can work and did work. And yes, it does rely for, let's say, its a percentage success rate and its durability on letting a fair bit of heat flow through that assembly by not using lots of insulation and by not having much of an air barrier. So that meant that you could put paper onto a wood frame house and it could survive 100 years. I've certainly seen that many times. But by the same token, is that if you put building paper behind, extruded polystyrene in a highly insulated R30 wall assembly today, when water gets there, it doesn't dry out as quickly. The paper can decay in a matter of a few years. And so you really, things have changed, and it's that change that explains why the paper is not as effective as it used to be. But we did know practically we needed to use drainage. It just was never in the design world, in the code world, in the standard world, was it ever discussed as you need to do drainage until the 90s or so that it began.
Yeah. There are a few questions here on the furring strips, maybe as a follow-up to what we were talking about before, and maybe I'll just kind of rattle them off and you can kind of address them. One is, recommendations on furring strips that are going over a high-density mineral wool. Is there any preference on how to address that from a sizing or material perspective?
Look, I mean, people use 1x4 or occasionally 1x3s the most. And that's just because they're widely available and relatively inexpensive. Other people, like on the West Coast, where you have concerns that it might be really wet for a long period of time, people use pressure treated 3/4 inch plywood, pressure treated, cut into 2.5 inch wide strips, that kind of thing. And whether it doesn't really matter much if you're doing it over foam or using 4-pound stone wool or 8-pound stone wool, it's pretty much the same answer. It just depends a little bit more on your trade craft of installing them. Having done it myself a fair bit, I can, there's a difference when you install them, but it's totally doable and it's just not that big a deal. The biggest questions come out in the commercial sector where we're using multi-story buildings. We're worried as much or maybe more about wind suction causing the failure of furring. And that's where we're thinking about using metal hat channels and specialty extrusions and so on to be able to accommodate movements, accommodate wind suction, meet fire codes. And that's when we get into a whole world of different types of furring solutions.
Gotcha. So a question here about wood furring on a 45-degree angle. There's not a ton of clarity there. Maybe you can interpret that.
Oh, yeah.
I'm envisioning a roof where we're talking about 45-degree angles.
No. 45. It's not just about vertical furring and horizontal furring. My bad for
diagonal.
Applying that. Smart people well before me said, yeah, I know it. You don't want to do horizontal because it traps moisture. But what about 45? 45 does a really good job, but it just requires a little bit more tradecraft. I used that word earlier, right? You got to get the trade on side. I've absolutely seen it done more than a few times. and it does work. I also have seen it done on a commercial, on an 11-story building, more than one. And it's a system they use for various benefits, not just the water side of things, but has to do with adjustability and so on. So 45 is definitely an option that's worth investigating. As soon as you're a lot off of horizontal, water will run down and away. And that's the key thing here, right? Nothing beats vertical, but if you got a good 45 degree, that water is going to run away. And that's what you want.
Okay. Well, I think we hit a lot of the major ones. I know we're now 15 minutes past. John, I don't know if there's anything else that you want to bring up.
Well, here I'm just looking. I'm able to go look at
Yeah.
the Q&A now, but Scott Witt asks, is the vertical movement of air in the gap what drives the space versus just having the airspace? Before I go on to the rest of that question, I'll say yes. The airspace does essentially Zippo in terms of improving drying. It is air movement in that gap. And, even if it is moving around within a gap that's sealed, it helps a little bit, but really it is opening that gap up to the outside. And in a lap siding world, it is opened up to the outside, either by unsealed laps, if you don't overpaint it or use slightly rougher, or by having air open at the bottom and the top. And I strongly recommend that latter. Put it over furring strips, open it at the bottom and the top. It does make, and again, this is not just my opinion. We have good measurements that show the significant beneficial effect of having airflow enter at the bottom, leave at the top when the sun warms it up, takes the moisture off, heats that air up, runs a chimney, and you get some significant drying. That's where you get the huge benefit. And I think Scott mentioned a 1/4 inch. You see, that's kind of the thing, is that 1/4 inch is actually, some people would say, is a small gap, but it already makes a difference. In the scenario of lap siding over wood framing in Austin, that 1/4 inch is a huge step up from the 0 inch. Is a 3/4 inch better? Yes, but I bet you it's a marginal improvement in that system. It won't make a big difference going from a 1/4 to the 3/4, but going from 0 to 1/4, big difference.
One of the questions here, John, is just climate zone here at the end. And when do we need to rely on Rainscreen as best practice? Are there specific climate zones that we need to be more cautious
first of all,
than others?
I think the key thing is that be careful that it's not just about climate zone, because if you're in Kansas City, Missouri, and you're building a 12-story building that's not surrounded by a whole bunch of 2- and 3-story buildings, you have a lot of exposure to driving rain. Now, whereas if you're building a single-story house with a veranda porch around 2 sides of it and big overhangs on the other 2 sides, you're seeing almost no rain. But they could both be address Kansas City, Missouri. So exposure is more the driver. And the other thing I've already hinted at is, what's your cladding system? If you're doing a brick veneer, you probably don't need to worry too much about drying out the brick. If you're in Arkansas, that philosophically different place that was introduced at the beginning, so that brick is able to get wet and it takes it, no problem. But on the other hand, if I'm in Austin and I'm using wood siding, it's like the wood is actually going to be damaged by excessive times at wet and too much wetting and drying swings causing movements. And so that's when I say, well, for wood, I'd use furring strips in most houses just to minimize maintenance problems. But if you're doing a high-rise building and you have a brick veneer, well, you could probably get away with just drained and you don't need to worry about ventilation, even though ventilation helps.
How about spray foam, John? Can that be considered as a WRB from your perspective?
It can be, and it is used in some areas quite widely. Just be aware that the product itself isn't the problem. It's all about how you're going to detail the joints. So all those transitions at floors, at shelf angles, at window penetrations, at et cetera, that's where you need to get good detailing. And you're often using a membrane to make those transitions and then spray foaming up to those membrane spots. But it is and can be used.
Dylan also had a question. You were talking about the horizontal hat channels, and I believe you referenced a perforated hat channel that will drain water through the perforations. I guess there might be circumstances where that hat channel might be angled and the water might be draining down the back side of that towards the siding, or the back of the siding towards the wall, or I guess maybe to the siding. But is there concerns about water pooling in, between the siding and the hat channel?
But that's what the perforations allow the water to leak down. So by perforations here, I'm typically talking something like 1/8 diameter holes, maybe 3/16, and they're pretty close to the edge, so that water runs down, gets to a hole, and if any hydrostatic pressure builds up, it drops through the holes. So you could try by test, right? Buy some of that stuff or have them send you an example. You can pour your beer pitcher down there and find out if it drains.
Yep. Well, this was great. I mean, there's a question here from Todd Noyce about educational resources that you'd recommend.
Yeah, that's pretty hard. Oh, he also has one there about applying paint. Well, it's sheathing, first of all, not sheeting, it's sheathing. And you can use a fluid applied air water barrier, but I wouldn't just use paint because paint doesn't have very good crack bridging capabilities. And so that's the reason why we have fluid applied air and water barriers made of a whole range of products, including STPE, as you mentioned, and then entangled mesh. And then, that's completely what's expected for those mesh products. That's what they're looking for.
All right.
Whew. There. And so I hope people have gotten their answers for how they get their credits and stuff like that. Or I don't even know the answer to how do we find the Google Raina webinar series or something. I don't know if there's something on the RDH site, but I know it's on the Raina site somewhere, right, Todd?
Yeah, I think we post the programs on the Raina site, www.raina.org. You might need to email us about getting the credits for watching it virtually if you wanted to kind of revisit that. I don't know the answer to that offhand. So you can reach out either to RDH or to Raina, and we'll be able to get you those answers.
Cool.
Very good. Well, thank you, John. I really do appreciate your participation today and your inertia and energy. Really good stuff.
Glad to do it. The fact that people care about what I care about is just astonishing to me.
Yeah, almost 300 people.
All right. I'm going to go tell my wife that what I do is not that nerdy. There.
Very good. All right. Well,
all right.
thank you so much. And thank you everyone for attending.
Bye-bye.